All right, so we've talked about different plate boundaries. We've talked about convergent, divergent, transform plate boundaries. And these are sort of geologic uh, structures, geologic features on, a more global scale. Now we're going to talk about features that are formed, in a similar manner, may look similar, but happen on a much more local scale and often, within a tectonic plate rather than at the boundary. And to address this, we really have to talk about the difference between confining pressure and shear stress, something we sort of touched on in the metamorphic section, but now we'll more formally talk about it. Confining pressure or lithostatic pressure is a situation where the pressure on the rock is the same in all directions. Just think of a rock being buried maybe 10 kilometers below the Earth's surface, and it's under a lot of pressure due to the weight of the rock above it and the rocks beside it and the rock below it, but there's no direction that really exerts more pressure, more force on the rock. Shear stress, on the other hand, a condition with shear stress involves the forces being unequal in different directions. The pressure on the rock is greater in one direction than another. And we can have situations like tension, where the rock is being pulled, compression, where the rock is being pushed or compacted, and then we can have shear, like you have here, where the rock is sort of being torn sort of unequally. So those are forces that stress, and strain is a term that describes how a rock responds to stress. And this is quite important because different rocks respond differently to stress, especially when they're under different temperatures. For example, cold rocks closer to the Earth's surface generally, they're brittle. They tend to break. And when you exert shear stresses on these rocks, they'll break brittly, they'll form things like faults. When you exert tension on the rocks, you get a normal fault. You get a situation where the rock's being stretched out, and the rock, this wall here, sort of falls down the slope here. In a compression situation, you get a reverse fault. The rock is being pushed together, and you see this wall here goes upward above the other one. These colors here refer to the same rock as they were before. You see this yellow part is being pushed up. And the last situation where you get shear, you get a strike-slip fault. Sort of looks like a transform plate boundary, but on a more local scale. You get things moving laterally side to side. And then you can also get what are called oblique faults, where you have a combination of tension or compression or shear, some combination of those three situations acting to form an oblique fault. But that only applies when rocks are brittle. Hotter rocks, deeper in the earth, they respond differently. They have a different strain to them. They are ductile, so they won't break brittly. They will stretch and sort of deform to form folds, which we will talk about shortly. So here again we are with faults. This is just illustrates different types of faults. This is not a type of situation you'd likely encounter in the field. You see the strike slip or lateral type fault here. You see two normal faults facing opposite from one another. This is a common situation here where you have these lower blocks called graben and what is called horst and graben topography, where the land is sort of being pulled apart. Think of the basin and range in a place like Nevada. And then when you get the rock being pushed together, you get this reverse fault. And you can sort of look at the angle on the top block. If it's an obtuse angle like that, you have a normal fault. If you have an acute angle like that, you have a reverse fault on the top, the highest block here. And here again we are with folds. There's a lot of detail we could go into with folds, but for now I'll just introduce you to the syncline and the anticline. The syncline, it's sort of a bowl type fold that sort of curves downward and back up. And the anticline is the opposite, think tipping the bowl upside down and placing the open end downward. That is the anticline. And here's an example of the formation of an anticline, but also after it's been eroded. So if you see a pattern like this on a geologic map, you can think to yourself, oh, I see same type of rock, same age on both sides. Maybe this is a fold. And just as a side note, anticlines, because of their shape, they often trap oil and gas and sort of the top part here. So often oil deposits are found in anticlines, but there are other types of oil and gas traps as well. For the last part of this recording, we'll talk briefly about strike and dip, which are two numbers you can use to describe folds, faults, and other geologic features. The strike direction is a direction relative to north, that you have sort of a horizontal line along the surface of your rock layer. So your strike is completely horizontal, and once you find that horizontal line along your rock layer, you compare that to north. That is your direction, that's your angle. Then you draw a line perpendicular to that, that's your dip line or your dip direction. And then from that perpendicular line, you measure down until you hit the rock surface again, and that angle is your dip. So your dip is your sort of angle perpendicular to your strike that goes down again to your rock surface. And you can use this to measure and to communicate the direction and sort of steepness of folds, faults, and other geologic features, and you'll see this a lot on geologic maps, which we'll talk about in the next recording.